Hello dear students, welcome back to Easy Notes. Today we will be starting the part C of chapter 4, that is application of refraction of light, in which we will be studying the first application, that is real and apparent depth. Real and apparent. What is apparent? Apparent means something false. Okay, something which is not present but appears to be. Okay, that is known as apparent depth. So what happens is, an object placed in a denser medium when viewed from the rarer medium appears to be at depth lesser than its real depth. This is because of refraction of light. Why does it happen? For example, if you see a fish from a rarer surface, that is from above the water, the fish seems to be a bit higher compared to the actual depth. Actually, the fish might be here, but it seems to be here, somewhere upward, right? Somewhere higher. That is nothing but apparent depth. Why does it happen? Let's see. So let us consider we have two surfaces. This is a rarer medium, two medium rarer, and this is denser medium, which is of refractive index mu. It is of refractive index. So let there is an object O here, which is d distance from the surface. That is nothing but boundary. This is the real depth. Okay. Now what happens? There will be some rays coming out from this object, right? So these are the rays. Oh, these are the rays. Let us consider two rays are coming out like this. Okay. Now this is normal. This is what? This is normal. This is our normal. Normal and now what happens after refraction of light? As it's going from denser to rarer medium, it will bend away from the normal. So it will move away from the normal like this, away from the normal, right? So when we retrace these refracted rays, these are the refracted rays, right? When we retrace these rays, it will join at some point. There we can see our image. So let's retrace back. If we retrace these rays, see, they're joining at this point. Here we can find our image. So we'll see our image a bit higher from its real depth. So this depth is known as d dash, that is apparent depth. D is what? Real depth. D dash is apparent depth. So there is a relation between real and apparent depth. Apparent depth is equal to real depth upon mu. Mu is of denser medium, not rarer. Okay, remember, mu will be of denser medium. So we can write d dash is equal to d by mu. Remember this. This will be useful for solving numericals. Okay. Now what is this? What is this thing? This thing is a shift between apparent and real depth. So this is known as normal shift. Why is it known as normal shift? Because see, in previous lecture we have studied about lateral shift, right? Because it was displacing sidewise, but here it's displacing normally. There is nothing but perpendicular to the surface. So we are telling it as normal shift. This is known as normal shift. So what is normal shift? To talk about normal shift is normal shift. Normal shift is real depth minus apparent depth. Real depth minus apparent depth. Right, this is nothing but the normal shift. So normal shift can be written as real depth is d minus apparent depth is d dash. But for d dash we can write it as d by mu. So if I take d as common, so it will be 1 minus 1 by mu. This is the final formula for normal shift. Okay. So by this distance it will be displaced from its actual position, that is nothing but from its real depth. Okay. Next, the shift by which the object appears to be raised depends on what factors does it depend? First is refractive index of the medium, that is nothing but d dash, right? Mu. Okay. The thickness of the denser medium. More the thickness, more will be its refractive index, that is nothing but more will be the denser medium. The color or wavelength of light. On these three things it will depend. So dependence on refractive index, higher the refractive index, more is the shift. Simple, right? More will be the shift. Okay, normal shift will be more. Next, dependency of shift on thickness. Thicker the medium, more is the shift again. On both it is directly proportional. Directly proportional. Next, dependency on wavelength. The shift decreases with increase in wavelength. It is inversely proportional here. As the wavelength keeps on increasing, the shift goes on decreasing because refractive index goes on decreasing as the wavelength increases, right? Okay. Since mu v is less than mu r, there's nothing but refractive index of violet is less than more than refractive index of red. Therefore, the shift is more for violet light than for red light in the given medium. Okay, greater the refractive index, more is the shift. Greater the wavelength, lesser is the shift. Next, apparent bending of the stick under water. What happens? As soon as we put a stick inside the water, what happens is the stick appears to be somewhat bended, right? Why does it happen? See here, this is the actual. This is what this is actual. See here, this is actual stick. Okay, this is the actual stick. This is actual stick. There are two rays coming out from here, 1 and 2. They are bending away from the normal because it's going from denser to rarer medium. So if we retrace this, they are meeting here. So this stick will be somewhat seen a bit bended. Okay, see what happens when a straight stick or a pencil is placed obliquely in water and viewed from the air. The part of the stick inside the water appears to be raised and shortened. It will be raised also shortened. As a result, the stick looks bent at the water surface. At that surface, it will look bended. So you can see by doing it practically. Take a glass water, water inside a glass, in a glass bottle, glass. Okay, कांच का glass. Okay, glass. Okay, so take a water inside it, put a pencil. It will be looking bended somewhat. Okay, this happens due to refraction of light from water to air. Light rays coming from this submerged part bend away from the normal. When they pass from water to air, these rays appears to come from a point above the actual position, forming a virtual image. So we see an apparent image above the actual depth. Okay, therefore the underwater part of the stick appears lifted, making the stick look bent at the surface of water. Done. Next, note point. An object placed in rarer medium appears to be at a greater distance from when viewed from the denser medium. See, why does it appears to be at greater distance? See here, the rays will come from here, right? The rays is coming from here this way. While going from denser to rarer, rarer to denser, it will bend towards normal like this. So when we retrace back, it will be somewhere here. So it will appear to be a bit higher from its original position. For example, an object in air appears to be higher when seen from inside water. Okay, whenever you will be swimming and you look upward, okay, the things you're seeing up is looking a bit higher from its actual depth, its actual position. It might be here, it will look for you here, somewhat higher. Okay, next, some numericals. A coin kept inside a water whose refractive index is mu 4/3. Whose refractive index is 4/3. When viewed from air in a vertical direction, appears to be raised by 3 millimeter. What is this? Appears to be raised by 3 millimeter. Appears to be raised by 3 millimeter. By 3 millimeter means this is the normal shift. This is what? Normal shift. Shifted by 3 millimeter, right? Find the depth of the coin in water. Okay, let's find the depth. So we know normal shift is equal to d into 1 minus 1 by mu. So normal shift is how much? 3 millimeter is equal to d. We need to find 1 minus 1 by mu is how much? 4/3. So we can write it as 3/4 because denominator becomes numerator. 1 minus 3/4 will be 1/4. 1 minus 3/4 will be 1/4. So 3 into 4, 12 millimeter. Depth will be equal to 12 millimeter. Easy. Just need to cross multiply here. Next, how is the critical angle related to the refractive index of the medium? How is the critical angle related to the refractive index? No, we haven't learned this topic, so we can skip to the next question. Okay, let's see. A pond appears to be 2.7 meter deep. This is appears to be. There is nothing but apparent depth. How much? 2.7 meter. If the refractive index of water is 4/3, mu is how much? 4 by 3. Find the actual depth of pond. We need to find d, not d dash. So we know that d dash is equal to d by mu. So d will be equal to mu into d dash, cross multiply. So d is equal to mu is 4 by 3 into 2.7. So 3 ones are 3. 3 into 0.9 will be 2.7, because 3 into 9 is 27, right? So 0.9 will be 2.7. So d dash is equal to 4 into 0.9 is 3.6 meter. Yeah. It is actually 3.6 meter deep. Yeah. Next. The apparent depth of liquid in the vessel is 15 centimeter. D dash is how much? 15 centimeter. Okay. When its real depth is 20 centimeter. D is how much? 20 centimeter. Find its refractive index. You can find mu easily. So comment down the mu of this question. Question 3. Okay. Let's see the last question of this chapter. Of this part. A rectangular glass block of refractive index 1.5. Mu is how much? 1.5. Mu is equal to 1.5. Has an air bubble trapped inside as it's shown. Okay. In the diagram, when seen from the surface AB, when seen from here, it appears to be 4 centimeter deep. This distance is how much? This distance is 4 centimeter. This is D dash. D dash is how much? 4 centimeter. So calculate the actual depth from surface AB. So let's calculate for sub question A. D is equal to mu into D dash, right? Just now we did. So mu is 1.5, D dash is 4. That is nothing but 6 centimeter. Actual depth is how much? 6 centimeter. Done. For which color of light, blue or yellow, the apparent depth will be greater? Apparent depth will be greater. See, we know that D dash is equal to D by mu, right? So we can say here that D dash is inversely proportional to mu. But mu is also inversely proportional to wavelength. So ultimately we can say that D dash is directly proportional to wavelength. Greater the wavelength, greater will be the apparent depth. So in VIBGYOR, which has a greater wavelength? LO has a greater wavelength. So therefore D dash of LO will be greater than D dash of blue. This is the answer. Part B. Is it? Okay. Next. Turning the glass block upside down does not change the apparent depth of the air bubble. Straight, true or false? If I turn this upside down, what happens? If I turn this upside down, this total is 15. Right? Somewhere here, there will be an what? Air bubble. Okay. The actual depth is how much? This actual depth is 6 centimeter. 6 centimeter from where? From AB. It was where? From here it was 6 centimeter. Okay. Here it was 6 centimeter. This is AB, right? Because we turned it upside down. So from here it will be 9 centimeter. So if D changes, so D dash will be D by mu. D is 9. Divided by mu was 1.5. Right? 1.5 into 6 will be D dash. 6 centimeter. 6, 2, 4, 6, yeah. D dash will be 6 centimeter. But initially D dash was 4 centimeter. Next D dash will be 6 centimeter. So the statement was false. They told that the apparent depth does not change, but it will change. Okay, why? Because real depth is changing, right? Okay, done. So we have been completed with the part C. So in next lecture we'll be starting part D. Till then, keep supporting us and keep following us. Bye bye.